We ended the last video by discussing the convergence of the Jacobi and the Gauss-Seidel methods. An interesting feature of this convergence is that it depends entirely on the matrix M obtained from inverse of Q times P, and in fact it has nothing to do with the initial guess X. If the infinity norm of this matrix M is less than 1, the solution will converge from any initial guess. Since the matrix M is determined by the components of the coefficient vector A, the matrix A is very important for determining whether or not a system will converge. One characteristic feature of systems that are poorly conditioned, that is, have difficulty converging, is that when small perturbations or errors in the coefficients lead to large changes in the solution vector. If this is the case, then we call the system ill-conditioned. A system that is well-conditioned is one for which small errors or perturbations in the coefficients result in small changes in the solution. Well-conditioned systems are much easier to solve because the convergence leads us closer and closer to the true solution. Ill-conditioning can be described by multiple features that are easy to identify. If the determinant of the coefficient matrix A is small relative to the largest values of the matrix A and the vector B, then the system may be ill-conditioned. Furthermore, if the elements of the inverse of A are large relative to the elements of the solution vector X, then the system may be ill-conditioned. An analytical measure of how well conditioned a system is called the condition number, kappa, of A. And when kappa is much greater than 1, we say the system is ill-conditioned. The condition number kappa is defined by the product of a matrix norm of A and the same matrix norm of the inverse of A. This can be calculated using any of the matrix norms, but should use the same norm for both A and its inverse. If you use a different norm, you'll get a different condition number. Condition numbers can also be estimated from the ratio of the absolute values of the largest and smallest eigenvalues. If that ratio is large, the system may be ill-conditioned. When a system is ill-conditioned, there can be a large relative error in the computed solution. If we call the computed solution, or the solution that we've converged to after using one of the iterative solution methods, x sub c, and the actual solution, x sub a, then the residual vector is the difference between the actual solution and the computed solution. That can be obtained by axc minus b. And the relative error can be expressed as a scalar value if we take the difference between the computed solution and the actual solution, find its norm, and divide that by the norm of the actual solution. This relative error always lies between the ratio of the norms of R and B divided by the condition number and the ratio of the norms of R and B multiplied by the condition number. So when the condition number is close to 1, the relative error has a very small bound. However, when the condition number is much larger than 1, the lower bound and the upper bound are very far apart from each other. And so we can have a large range for our relative error. After we've found a computed solution, x sub c, we may calculate our condition number, and that can tell us something about the error bounds on our solution.